to start off, do we have any SonicWall lovers in the room? Oh, we do have one. Interesting. Any SonicWall haters? So mostly agnostic people. So I'll see whether I can shift your opinion on that before lunchtime by going through the presentation here. So a little bit on myself quickly. I'm currently the head of research and development at Orange Cyberdefense in Switzerland. But essentially, I've been a pen tester for over 15 years now, so working in offensive security. I do some vulnerability research, but it's not necessarily my primary focus. Though some of my colleagues often come up to me asking me, do you know a vulnerability in this solution or that solution? Most of the time I don't, but I tell them, well, I can actually have a look for it. So that's how I end up with these kind of topics. I also happen to organize our own conference, Insomniac, in Switzerland, just a little bit of promotion for us as well. But otherwise, why am I talking about this today? Well, unless you've been hibernating under a rock somewhere for the last 10 years, you've probably noticed that there rarely goes a month or two without some kind of serious vulnerability affecting one of the commercial-grade VPN vendors, be it Fortinet, Palo Alto, Checkpoint, F5, SonicWall, pretty much whichever one you can think of. They've had one or multiple vulnerabilities affect them, and not just poor vulnerabilities, they're actually security, very critical vulnerabilities in there. Most of the time, they'll be reported by Watchtower Labs because they write hilarious blog posts criticizing these solutions. Definitely recommend reading them. But that kind of got me thinking as to, it's kind of sad that these solutions which are supposed to protect us actually end up being the reason why companies get breached, because they have vulnerabilities in them. So I thought, well, why are we in this state? And why is it not really getting better? I mean, I don't think the security of VPN solutions nowadays is much better than it was 5 or 6 years ago. And I think one of the reasons behind that is probably because people have a tendency to think that they're all equally bad. So you look, I have this solution, okay, there's a vulnerability in it, I'll patch it. But all the other solutions also have vulnerabilities as well. So should I really change? Does it really change anything? So that got me started on this research project where I wanted to kind of find a way of comparing these solutions and determining whether one was better than the other. Unfortunately, I kind of got distracted a lot by actually searching for vulnerabilities rather than just comparing the metrics I wanted. But one of the more naive ways of doing this was looking at the number of CVEs affecting the different vendors. So for anybody who's actually looked at CVE information, it can be quite tricky to get what you want out of them. But wanted to give an idea of how long or what duration there is between two critical CVEs within a solution. So I highlighted here the one from SonicWall, which seems to be somewhat around 150 days between two critical CVEs. I'm not sure how accurate this data is, but it's what I got out of some research into CVEs and so on. But you can see there's quite a difference between, I don't think you'll be shocked to see Avanti up here with a little more than a month between two critical CVEs, all the way down to Checkpoint, where we're nearly at three years. So there's already a large discrepancy here between the different vendors, but I'm not sure that necessarily means that one solution is better than the other, because oftentimes people just search for vulnerabilities in more popular products, and you'll discover more vulnerabilities, or maybe you'll actually get CVEs, whereas in other cases you might not. I mean, there are lots of reasons why you might have more CVEs in one product than another. So instead of just looking at this, I kind of wanted to look at how these solutions actually protected themselves from attacks. And specifically, I was looking at memory corruption vulnerabilities. So I wanted to see how they protected against these. Kind of broke it down into two different categories, and I'm not showing the actual results for each vendor because I'm not completely convinced that they're perfect yet. But essentially, I broke it down into code hygiene and security features. So code hygiene would be like, what does the code look like? How dangerous does it look? How often does the application or this appliance use dangerous functions, like string copy, system, and so on? And the security features are how many mitigation features do they actually implement to protect from memory corruption, so ASLR, DEP, stack canaries, and so on. And interestingly, SonicWall did not come up very high in the list here. Specifically, in the code hygiene score, I actually had to restart or rethink how I was computing this, because I found results for all of the vendors with an initial formula, and then came up with SonicWall, which kind of destroyed everything because their results was so much poorer than all the others. So I thought, well, it's probably an interesting research project to kind of search for vulnerabilities in SonicWall, given how the code felt, essentially. So I took a bit of time, got a trial virtual machine from their website, which is practical. You can just go download them from their own website, install it on my laptop. At the time, the version was whichever version is up here, which was the latest one that was available at the time. So, booted it up. What does it look like? If you want to look at the attack surface, essentially from the network, there are two ports which are open, port 80, 443, standard web application. And the CLI itself looks like something like here. So you don't have direct shell access. You can't execute arbitrary commands on the device, which is kind of annoying for someone who wants to do a research project, because it's very practical to be able to execute what you want, to debug things, access the file system, and so on. So the first step of my research was try to gain access to the file system, gain full access to the system itself. And I started searching for like command injection vulnerabilities in the CLI, because that surprisingly works quite a lot. But I didn't find anything straight away, and instead I used a fun technique that one of my former colleagues showed me, which is manipulating the memory of the virtual machine itself. And I wanted to try and demonstrate this live rather than show it on the slides, because I'm sure everybody likes live demos that may or may not work. So I have, that's not right. You don't see my second screen. Let's see, I'll just bring it back to the other screen then. Like this. I can do it from the same screen, I think. So I have my VM here, the virtual machine. I can just pause it, which will create a memory file of the state of the machine, like this. And then I can come and edit the memory. So to get the right one, let's be this one over here. Being an elite hacker, I do it with Notepad. So it's a somewhat large file. It's like 4 GB file. I'm just going to replace any occurrence of this string here with a shell command. So here we go. Perfect. I just want to make sure it's the same length, because otherwise VMware won't be too happy. I just replace this everywhere in the memory file. And yeah, replace 9 occurrences. Perfect. Save the file. Takes a couple seconds. And if I come back to my virtual machine over here, I can just start it again. Yeah, not a problem. Log in. And the one I targeted is the restart SSL VPN services. I click this here, click yes. And if everything went well, I now get my root shell. Nice. So that actually works surprisingly well in a lot of cases on many of the different devices I tested. So there's nothing to do specifically with SonicWall, but it is one way of getting root on a device when nothing else works, essentially. So that's just kind of showing these two slides off here. So once I had my root access, I continued analyzing the attack surface, looked at what just kind of verifying that the open ports that I had from the network, there was nothing else there. Kind of summarizing this here, we have the 2 web ports here, and another one listening on the local interface, which happens to be a Python Flask API, which I then found through the different PS commands, just seeing what was running on there. So we essentially have an Apache server listening on the web ports, and then the Flask API, a Python Flask API, on a local host interface. And when you access it from the network, it looks like something like this. So if you've ever seen a SonicWall device, you probably have seen this web interface here. So I started off looking at how Apache was configured. and came up with something like this. It's sort of a simplified overview of what's going on behind the scenes. So you have your browser here connecting to Apache, and depending on what kind of URL you're hitting, it will go through different things. There are 3 special prefixes which will end up calling a custom HTTP RP module, which I suppose is reverse proxy module, and we'll get to that a little bit later. We have some that directly call a number of Python scripts, and then you have the CGI bin folder, which just calls a number of C, C++ CGIs. And of course, all the rest are just kind of static files here. So initially, my main focus was looking at memory corruption vulnerabilities, and seeing a lot of C, C++ CGIs kind of drove me into looking further into these. And I wrote a small tool, which I just released earlier on GitHub, which kind of helps me search for the use of dangerous functions, that I'd call them, like occurrences of string copy, sprintf, things where they're not checking the bounds on the buffers and so on. So it's based on the Ghidra API. It will just kind of decompile the binary, search for any locations in there where there might be something a little bit dangerous. And it outputs something like this. Here we can see, for example, that string copy is used multiple times in different functions. So if you're lucky enough and you have debug symbols, you can actually figure out kind of what the function does and determine whether there is a chance you might be able to reach it from the web interface or not. So this is kind of how I went through all the different CGIs, looking for vulnerable calls. And I don't know if it's surprising or unsurprising, but there are a lot of these potentially vulnerable things. So obviously, using string copy or one of these functions does not mean there's a vulnerability that's there that can be exploited. But it is kind of dangerous, right? Why not check the bounds of your buffer before copying if you can? So I kind of tied all this up with another little tool which looks through all the different binaries on the system and seeing how they're interlinked, just kind of looking at the exports, the imports of different files and seeing which binary uses which library and so on, which I also just put onto GitHub a little bit earlier here. The idea was to look, well, within the user login, for example, CGI, I'm using all these different functions which come from other different libraries and so on. So it kind of just helps me map what's going on the device, pretty much. So unsurprisingly, I quite quickly found a number of memory corruption vulnerabilities here. We have one heap overflow in SonicWall's CGI. Not super interesting in the end because it requires authentication, and most of the time, it's not really what we're looking for. But just to see how trivial it is, we have a variable up here which is allocated with OX80 size. We get a argument from the URL, essentially, which is OX400 size. We do a couple string manipulations here and end up string copying it into the smaller buffer over here. So it's very, very trivial, obvious vulnerability. You can trigger it with a request such as this. You just have to be larger than OX80 size. Being a heap overflow, I'm not initially a binary exploitation guy, so I'm not very good at exploiting these issues. So I didn't actually find a way of getting code execution through this. And given the fact that it was post-authentication, I didn't actually spend too much time looking at it either. But I found a number of other interesting findings. One of them is that there's one specific library, libsys, which is used kind of throughout the code base, which defines a number of encoding functions, like JavaScript encode. You can imagine like HTML encoding characters to print them into a file. Now, interestingly, you have kind of the code here. It doesn't actually check for the bounds, or it doesn't check that the resulting buffer is within the size of the output buffer that you're providing it. So it's kind of expecting that the calling function will do this instead, which obviously is not really the case. And these are called throughout the code base. In unauthenticated CGIs, authenticated CGIs, there are dozens, if not hundreds of occasions where you have overflows because of this. Now, I reported some of them, and I'll talk about that a little bit later, but I'm convinced that there are a lot more issues that I didn't necessarily investigate too much here. So one of the interesting occurrences I found was in an unauthenticated CGI called CIFS Navigate, which, why it's accessible without authentication, I don't know, because it kind of gives you a sort of graphical interface to navigate a share. So no authentication required, very similar to pre-4. We get a parameter from the URL, OX400 size. We do some string manipulations in here to kind of figure out what the share is, what the server is, and so on. And eventually, we use the double escape special, I like the naming of it, function on the input, and we store it into a destination buffer, which is actually smaller than the original input buffer. So even if you're multiplying by 5 the size of the buffer here when you're encoding it, it's not actually necessary to overflow the buffer. So again, a very trivial vulnerability. This time it's a stack-based overflow, and accessible without authentication, which is always cool. So was I able to directly exploit this? Well, there are a number of exploit mitigations on the system. So I don't know how familiar you all are with binary exploitation and mitigations, but there can be a lot of protections to prevent the exploitation of buffer overflows. Some of the more common ones we have here, so address-space layout randomization, which is the idea of having your different libraries mapped at random places in memory, so you don't know where they are. Data execution prevention, which prevents executing the stack, for example. The one I want to mention here are the stack canaries, which is the one that kind of annoyed me here. The idea is that whenever you're calling a function, you're going to be putting the return address onto the stack, and then you add a random or an arbitrary canary on there, so that if somebody actually overflows a buffer, they cannot take control of the return address and the instruction pointer without destroying the canary. So that's the idea. And that's unfortunately for me, or fortunately for SonicWall, what they had in place on most of their CGIs. So you can run a tool such as checksec, which will look at which security features are implemented on which files and so on. So it just kind of gives you a little sneak peek at that here. The fact no canary is found does not necessarily mean that the canary is specifically lacking. It's just that compilers don't always add the canary if there's no reason to. So in most cases, canaries are actually there, and there's no trivial way of getting around this. So technically, there are potential ways of getting around this, especially because of the fact that in this case, it's a 32-bit Linux system. And in that case, a canary is actually only 24 bits of entropy. It uses 3 bytes followed by a null byte. The null byte is there because it is the terminating string character, so that if you have an overflow with a null byte, it will essentially stop at the null byte. And unfortunately, within the code base that I was searching for, pretty much all the vulnerabilities I discovered, all the stack-based overflows I discovered, used string functions, so string copy, sprintf, strn copy, and so on, which made it impossible to actually overwrite the stack canary. So I could have potentially brute forced it, but I couldn't actually write the value I wanted in there. Potentially, what could be possible is if you have multiple successive overflows, or consecutive overflows, you could actually overwrite the canary and then with a second one, insert a null byte into the correct location. It might look like something like this, or we have multiple calls to the vulnerable function. So technically, this is probably exploitable, but I didn't actually go in too deep into this one because it requires admin access already, and I never actually figured out how to get to this part of the code in the appliance itself. So pretty sure there are other places where it might be exploitable, but I didn't actually find them directly. So I kind of abandoned the idea of looking for these overflows for a little while and expanded the research surface to look at other things, the Apache configuration, authentication, which was done to the different CGIs, to the Python APIs, and so on. So one of the interesting things that I discovered here, and probably the most important finding I had in the end, was that the Apache configuration on SonicWall was vulnerable to the path confusion vulnerability that was presented by Orange Cy at Black Hat last year. So I don't know how many of you are familiar with that. But essentially, Apache modules will all consecutively parse the HTTP request that's coming in, and they don't all parse it in the same manner. Shocker. Which leads to some inconsistencies, and in certain cases, they can be exploited to do various things. One of them, which is especially fun is when you have a rewrite rule such as the one that we have here. So if you're rewriting everything that's in /html/something to /something.html, there's an interesting quirk in Apache, which was if you actually access this page, you'd think that it should go search for the file down here, but actually it would look in both locations, either within the doc root or at the root of your actual server, which is pretty crazy when you think about it, because it allows you to read somewhat arbitrary files outside of the doc root. Now, there's one requirement, or two requirements, I guess. One of them is that you need a rewrite rule such as this. The other one is that you have to actually have like a directory set up in the Apache configuration somewhere, which does not deny access. So it doesn't have to explicitly allow access, but it doesn't have to deny it. Now, thankfully, in SonicWall, we have a nice directive which is up here, which takes the root of the appliance and does not deny access. So great. So that requirement is fulfilled. And the second one is this nifty little CSS rule. You actually have the comment saying exactly what it does. But essentially, it strips off the version number from the CSS file that you're loading. So I'll try and demonstrate this again here. See if, oh wait, no. Like this. Sorry. So here we go. Perfect. So this is kind of the original request. You'd have a request done to fileshare.version.css. And what happens is you can actually trick this by writing the .css here and then adding a %3s, which is a question mark, add a dot, and it will still load the same file. Will it? Yeah, perfect. I'm still loading the CSS file. And this kind of proves that the vulnerability is present. Obviously, when this worked, I was like, oh, great. Let's try and read etc password, for example, because that's what everybody does. And that doesn't work. It actually has nothing to do with the vulnerability itself. It's a different protection in Apache, in this case, or in the configuration they have, which kind of blocks access to anything that starts with etc. But that doesn't really matter too much, because there are a lot of other things, interesting files on the appliance, which are not in etc. One of them being a SQLite database, which is in /tmp/temp.db, which contains all the authenticated sessions. I'm not sure if I can necessarily find them in here. But somewhere here, you have the basic C4 encoded session information of anybody who's connected. And this is obviously accessible without authentication. You can access this URL and immediately then circumvent authentication, compromise anybody's account who is connected to the device. So that was pretty sweet. Maybe even more interestingly for me, when I was searching for this, was that you can also recover the Apache logs, the same kind of URL here. And within the logs, oh yeah, we don't actually see them here. Within the logs, I'll show them afterwards. Apache will have a detailed stack trace of any memory corruption. Memory corruption, essentially. I'll have it on the slides. There we go. Slides again. So, as an example of the file share, the etc password doesn't work. The SQLite database, which you can then just kind of, once you've downloaded it, you can access it like any other SQLite database, recover the sessions from here. But the other interesting file was the HTTPD log, which stored stack traces of anything that went wrong. So when you crashed the program, you'd have a dump, essentially, of the memory here, which, importantly for me, had the memory addresses of all the different modules in there. So if you've done any binary exploitation, having a memory leak or an information leak is pretty much required to be able to bypass ASLR or PIE. And in this case, this was great because it gives me pretty much all the information I need. So that's we'll keep that in mind for now and come back to the memory corruption later. But I kept on analyzing the authentication also to the application, to the web app, and noticed that there are various ways they can implement multi-factor authentication, be it through one-time passwords, certificate-based authentication. There may be some others as well. I don't actually know SonicWall all that well. But it seems like implementing multi-factor authentication is quite difficult. So I find a few different issues in here. One of them is linked to the one-time passwords. So if you happen to have set up your account with one-time passwords, a token which you use to log in, you can also generate backup codes, which is quite common. Like pretty much all applications will support generating backup codes. And they can be generated with a request such as this. You access CGI bin backup code, action generate, and it will give you the different codes here. So I looked at the code behind this, and it looks something like this. So can anybody spot what the issue is here? So they're essentially doing the one thing that you should never do when generating random numbers is they seed the random number generator with the current time. So the time in seconds, the epoch time here. So essentially, if you know at what time someone generated backup codes, you can know exactly which codes were generated. So it's a terrible way of doing things. Even more so because of the fact that the request to generate the codes does not have any cross-site request forgery protection against there. So you can actually force a user to generate backup codes at a specific time if you get the user to visit your own website or something like that, and then you'll know what the backup codes of that user is. So that was a fun little finding. Another interesting one is in the certificate-based authentication mechanism, which works something like this, or at least that's my understanding of how it works, where your browser will send the certificate information to Apache. Apache will check that you're actually allowed to connect, verify the certificate and everything, and then it will send off that information to the Flask API, the Python API, with this information in environment variables. That's relatively standard when you have a reverse proxy working in there. And then Flask would retrieve these parameters with this code here. Now, you'll notice they're using a module called request parser. And in request parser, there is one option that you can add to this, which is specifying the location of the parameter, saying essentially where you want the source of the parameter to be. So you notice some of the ones here specify that it has to be from the environment. But in this case, it doesn't specify that. And what that means is that you can actually just send these parameters in the post request when you're logging in to tell them, well, actually, SSL client verify is success. It's encoded in base64, but that's what we have here. And you can encode your own subject DN and your issuer DN in here as well. So you can completely bypass the certificate-based authentication by essentially telling the Flask API that you are authenticated correctly, which I thought was pretty cool. So going a little bit further, this reverse proxy module I thought was very interesting because it essentially allows users to access websites through the SonicWall device. So it really functions as a sort of reverse proxy. The URLs will look like this, /go/ pretty much whatever you want here. And at least in the default setup, there's no kind of firewalling, so you can access things that are behind the device or on the internet or wherever you want. I expect that in more productive environments, you probably wouldn't have that. But as it stood in my test environment, I could pretty much reach whatever I wanted through here after authentication. And this reverse proxy module also supports single sign-on. So if the backend server you're trying to reach requests authentication, it will automatically try to authenticate with your credentials. So relatively standard reverse proxy features there. And so I kind of dug into this, used the same tooling I had for the CGIs, looking for potential dangerous function calls. One that caught my attention was this specific function here, which is related to how the server deals with responses from backend servers that request digest authentication or NTLM authentication, because there were references to str and cat. Now, it turned out that there was nothing to do with str and cat here, but in this specific function, the reverse proxy module will get the authorization header from the server, strip the NTLM part, and then decode in base64 that value into a static buffer, which is the one which is here, so 1076 bytes. And unfortunately, the base64 decoding will not check the size of the output buffer. You're supposed to call another one, which is APR base64 decode length here before doing so. But what this allows us to do is not only overflow the buffer, but since it's actually decoding in base64, we can actually start writing null bytes now into the right places to bypass the canary protection. So now we have pretty much everything we need. We can, as I mentioned, the stack canaries can now somewhat be bypassed because you can write the null byte by base64 decoding. There are only the 24 bits of entropy, which means that there can only be like 16 million different canary values, which may seem like a lot, but if you suppose you can do 100 or 200 requests per second to a device, you'll be able to find it within a couple days, I think, something like that. I did some math yesterday trying to figure that out, but I think it's something like that. So for the other protections, address space layout randomization, or PIE, we can kind of bypass that with the fact that we're able to retrieve the HTTP log file and see all the base addresses in there, or all the memory addresses, which is cool. The only thing you need is to be able to crash the device once to get the stack trace in the logs, which is incredibly easy. There's another way of doing it here with this cookie, just yet another overflow memory corruption somewhere, which you can then recover in the log file. So kind of putting all of this together, I wrote a very simple kind of ROP chain based out of all kinds of gadgets that I found in libc. And this ROP chain just simply calls the system command with a reverse bash shell that we have here. So essentially, to be able to exploit this one altogether, you start off by leaking a valid session identifier from the temporary SQLite database. You generate a stack trace with any one of the overflows that I've already mentioned before. You get the libc base address from the log file. You create your ROP chain. You then spawn a fake web server, which will send your payload back to the appliance when you force the appliance to connect to it. So I've also put up a POC code up on GitHub. So I'm definitely not a particularly good developer or code writer, so don't look at the code too much. But I'll kind of show it in use here. So I still have my SonicWall running. Can I actually reach it? Perfect. So here we go. So I'm going to exploit this specific IP on this specific port. I'm going to ask it to connect back to my fake web server on this port here, and then that will trigger a reverse shell onto my machine on this port here. And we will see if this works. Looking good. Perfect. Hey! Thank you. So in this case, we're not actually running as root. We're running as the nobody user, it's the Apache user. But I'll let whoever wants to try find privilege escalation vulnerabilities in there. It shouldn't be too difficult. All right. So at the time, I did a quick look on Shodan to see how many potential boxes you could pop. There are about 10,000 of them online, mostly in the States. But there are a number of those that could have been exploited. I don't know exactly how many, because depending on the version, maybe older versions were not as exploitable, I don't know. But nevertheless, it doesn't give me much assurance as to how secure this device is. So for the timeline itself, so I found those in October last year, more or less. Reported them at that point. It took SonicWall, they actually responded quite quickly. Within a couple of weeks, they told me that the issues had been fixed. I checked that everything had actually been fixed. And then it took them another month, nearly, to actually release a patch. And I got a number of CVEs here. They kind of bunched all the heap overflows into one CVE and all the stack-based overflows into another, apart from the reverse proxy one, which was separate. But yeah, so I got a number of CVEs. I got a thank you message, and that's pretty much it. So if you're searching for bounties, I would not necessarily target SonicWall unless you're going to sell them on to somebody else, which I would not recommend, obviously. But yeah, to kind of wrap things up, it took them about, as I mentioned, 6 weeks to respond, which is a lot better than the last time I reported a vulnerability to them. It was about 5 or 6 years ago. It took them 6 months. So there's some improvement. But I think it's still kind of sad that we have security devices that are so vulnerable. I mean, we're in 2025 and we still have commercial-grade VPN appliances that have string copy used throughout their code base, which I don't think is normal. But I do somewhat understand the reasons behind that, because I think the incentives for vendors, and I mentioned security vendors, but all vendors pretty much, are not necessarily aligned with security. I mean, vendors want to provide cheap products so that people will buy them with lots of features and very fast. But unfortunately, that usually means that you're probably not going to have the best developers, you're going to have a larger attack surface, and you might disable security features so that things go faster. And that's what people look at when they're buying a product. You want something that's cheap, fast, and has all the features you want. So unfortunately, security is kind of an afterthought in many cases. So can we actually do better? I certainly hope so. I think one of the ways of doing this is kind of incentivizing vendors to promote the security of the products, if you will. What's been done up to now, it's kind of also what I've been doing during this presentation, is kind of shaming the vendors for doing terrible security. I don't think that works so well, because as I mentioned, I'm not sure we're much better off nowadays than 5 years ago, because of the fact that people just assume that other vendors are just as bad or just as good. So I think we have to find a way to actually compare these different solutions, which was kind of the idea of my initial research project, which is, I'll get to it at some point, finding metrics that you can actually compare between the different vendors and show that one is better than the other. I think there have been some developments on the legal side as well, where I think it could be an idea where you try and fine companies for selling you terrible products. And there's something that was changed in the Product Liability Directive, some kind of European law. I'm not a lawyer at all, so I'm not entirely sure about this. But like, digital software is now included in that. So if you have software that actually harms people, you could potentially be liable. So there are all kinds of ideas that could hopefully kind of push these vendors into doing a little bit better. So that's pretty much all I have for you. Thank you for listening. I put up the different code on GitHub. You have a blog post as well, kind of detailing everything I've talked about here. But otherwise, I'm happy to answer any questions.
So, do we have any questions from the audience? Don't leave, guys. We have very important stuff going on after the talk, so don't leave, stay put. Any questions? Come on, you can do it. Don't you dare have a question? Then I'll have a question. So, looking at really good talk and really good research, I share your I have the same idea. I have a really broken past with Juniper back in the day. So, do you think it's it's really expensive to develop products? That's what you yeah. And the gist of actually upgrading them is slow.
Yes, and we've kind of pushed the upgrade philosophy, like you're pushing your customers to upgrade constantly, so they have to buy licenses to get the upgrades. So you've kind of decided, well, they're going to pay for the security, right? They're going to pay for the updates and so on. So you're offloading completely the security to your customers, which is interesting that we've kind of accepted that.
Yeah, right? Really weird. So who's next on the list?
Good question.
Yeah.
So you have time to dig into other ones.
Yeah. No, really interesting. Thanks for sharing it with us.
Thank you.
Okay, don't leave, everybody.